Hello there, and welcome to today's webinar, Overcoming Ionospheric Scintillation Challenges for Precise Positioning in Automation and Robotics, sponsored by Inside GNSS, Inside Unmanned Systems, and Trimble. I'm Lori Dearman, Senior Webinar Producer with WebAttract, and I'll be one of your moderators for today's session. And in just a moment, we'll be introducing our panel of thought leaders who will provide critical insights into the solutions that can help ensure precise positioning even in the face of ionospheric disturbances. You'll have an opportunity to have your questions answered at midpoint and at the end of the presentation during our Ask the Experts panel session with all four of our panelists today. Now, we've invited you, along with over 350 professionals from 54 countries, representing a variety of industries. And over the next 90 minutes, regardless of your industry segment or your location, we're confident you'll find today's webinar of value. Now, before we get started, our moderator, Richard Fisher, publisher of Inside GNSS and Inside Unmanned Systems, would like to take a moment to welcome you and to introduce our sponsor for today's session. Richard?
Hey, Lori, thanks so much. Welcome, everybody. On behalf of Inside GNSS and Inside Unmanned Systems and our sponsor, Trimble, we're delighted for you to join this webinar. I'd like to begin by introducing Finley Wood, who's the General Manager of OEM GNSS for Trimble, for a brief word. Finley.
Hey, good morning. Thanks, Richard. It's a pleasure to be here with you all today. Over the course of this webinar, I'm really looking forward to sharing with everyone how Trimble and our partners are delivering cutting-edge technology that enables both autonomy and automation for our end-user customers. At Trimble, we focus on connecting the physical and digital worlds in order to support our customers in their daily work. We provide solutions in a wide variety of industries that touch all of our lives, from goods transportation to agriculture, construction, and a whole lot more. Our mission is to make our customers work better, faster, cheaper, safer, and greener. And today we will hear about some of our new technologies that enable this. We've seen a lot in the news recently about the Northern Lights and how beautiful they are and how they're being seen in areas not typically seen. And one of the technologies we'll hear about today is how the latest Trimble IonoGuard technology helps our customers mitigate the challenges caused by solar scintillation, closely aligned or similar to Northern Lights. We'll also hear from another of our customers about how they have brought fully autonomous tractors to market and the value they find in our RTX correction services. While Trimble is a large organization with multiple sectors and business units that serve different verticals, today you're hearing from the Advanced Positioning Group. We are focused on developing partnerships with OEMs and system integrators to provide GNSS positioning, components, and correction services for them to integrate into their own solutions. Reliable, high-precision GNSS is key to both Trimble's and our customer strategies. And at the core of this is knowing exactly where you are, anywhere in the world. Working with cutting-edge companies like Sabanto and Flanders is a real pleasure. My thanks to both of them for joining us today. And with that, I'll pass back to you, Richard, to get us moving.
All right, Finley, thanks for that introduction. This is today's panel. We have an excellent ensemble of perspectives from both Trimble as well as a couple of downstream customer perspectives that are kind of in the thick of it and really kind of proving these technology solutions out. So really looking forward to hearing from them. We will get to those momentarily, but first, Lori, we would like to have our first poll question. Lori, please.
Absolutely. And folks, coming up on your screen, you should have that poll question. We'd like to hear from each of you. Have you experienced an interruption in your GNSS that might have been caused by ionospheric scintillation? And curious to know, weekly, monthly, quarterly, annually, or maybe never, or you're not sure or don't know. Okay, well, we're coming in at 19% of our audience saying weekly, 17% monthly, 13% quarterly, 13% annually, and 37% never or unknown, not sure. Richard, any thoughts here?
Yeah, I mean, kind of as we expected. Frankly, I think it's a bit more frequent than what I had expected. Bottom line is 63%, a plurality of this audience is experiencing interruption that they believe is due to ionospheric scintillation, and in fact, 20%, which is very significant, are seeing it on a weekly basis. So the good news is there are solutions. We're going to do a deep dive now into talking about the problems, how to identify them, and how to mitigate. And our first speaker is Ed Norse, who's a portfolio manager for OEM GNSS at Trimble, where he helps guide the introduction of precision GNSS receivers into the geospatial, construction, agriculture, and autonomy markets. With extensive experience as both a land and marine surveyor, combined with his technological expertise, Ed has been a leading team member for Trimble's ongoing work to create advances in GNSS technology to mitigate the impact of said atmospheric disturbances on GNSS receivers. Ed, please proceed. Welcome.
Thank you, Richard, and welcome everyone to our webinar. I'm excited today to talk about Trimble IonoGuard. This is a technology that Trimble has been working on for a number of years now. And today I'm happy to show some positive results from RTK users around the world who are, have seen issues with high ionospheric activity. So just a quick look at what I'm going to do. I'm going to talk about the problem itself, what the problem is, and how solar cycles affect RTK users. I'm going to talk about the research and development Trimble has done to develop a solution. I'll talk about the solution itself, Trimble IonoGuard, and then some real-world results from around the world demonstrating the effectiveness. So this is a good slide I like to, as indicating the source of the problem. If you look on the left in 2019, if you were to look at the sun, I'm not suggesting you'd look directly at the sun, it's not advisable, but you would see very few sunspots. Today in 2024, we see quite a lot of sunspots, and this is due to a lot of high magnetic activity on the sun. During the 11-year cycle, near the end of the cycle, the magnetic field on the sun flips from one direction to the other, and this causes a lot of magnetic activity, a lot of it's known as space weather. And with this space weather, we get an ejection of solar radiation heading towards the Earth, which activates our ionosphere, the high part of our atmosphere. This slide shows the last 4 cycles, which really covers the history of RTK GNSS with this ionospheric issue. Back in 1990, that was quite a high cycle 22. We did not have many RTK users back then. We had some post-process users, I being one of them, which we were affected by ionosphere back then. We only had L1 GPS receivers in post-process mode. And then as the cycles came along, we had more users. Our users are more than doubling every cycle, which is an 11-year cycle, to today where we have a number of users in parts of the world we did not have back then. So as you can see from the graph, the predicted maximum for cycle 25, which is the one we're in right now, is in about July next year. And it was originally predicted not to be a very large magnitude. We're actually seeing it coming in a lot larger than expected, which I'll talk a bit about what we're seeing so far. Basically, as the radiation comes from the sun, we're seeing the ionosphere heat up. Our GNSS signals are passing through the ionosphere, and they're being degraded. And this results in positioning errors. With RTK, we're trying to get down to centimeter level, 1-2 centimeter accuracy. But when the ionosphere is particularly bad, this is degrading to the tens of centimeter level, which is not acceptable. So whereabouts do these ionospheric problems occur? It's basically in 2 regions of the world. And the main region where the people who are probably saying weekly on our survey are the people along the geomagnetic equator. South America in particular, we have a lot of mining and agricultural customers there who are seeing effects of scintillation is the main issue there. In the evening hours after sunset between September and March, we see a lot of activity, and there the RTK is having difficulties getting down to staying at the centimeter level. Also in northern latitudes, and this is mainly following these storms that we get occasionally, and depending on the level of the storms, the latitude will lower. So for very large storms, we do see issues in mid-latitudes in the US and Europe. And what do these issues do? They cause poor signal tracking. We see degradation in the actual signal-to-noise ratio of the received signal. We see measurement errors. And the graphic on the bottom right there sort of indicates a good indication of the problem we see with scintillation. The ionosphere with scintillation over the equatorial regions causes bubbles, ionospheric bubbles. And our base station, the whole premise of RTK is that we're assuming the errors at the base are the same as at the rover. And if the signals are passing through different parts of the sky, one satellite might be coming through a bubble. At the rover, that same satellite is not coming through the bubble. So we're not canceling out the errors, and we're getting these position errors. As you can see from the plot in the middle, we get hit by the ionospheric scintillation, and we see decimeters of errors in our position. So what has Trimble done about this issue? Well, we had plenty of advance warning. We knew the cycle was going to hit us maximum in 24, 25. So we put together a kit of material which included raw an RF recorders that's capable of recording raw RF, plus GNSS receivers. It's not good enough just to collect GNSS data because those signals have already been degraded. We need to record the raw RF data where we can then replay that data back into our receivers, tune the receivers both at the RF level and at the algorithm level to identify and remove ionospheric issues. So we've deployed these setups around the world in areas of high ionospheric activity. We recorded through some solar storms, and then we were able to tune our receivers and then reload new firmware back into the receiver and see if when we had the next storms, how the receiver behaved. And at that iterative process, we were able to develop our IonoGuard technology. This block diagram just shows you the different parts of the receiver. It wasn't just the algorithms, it was also the RF ASICs that we had to improve that code to improve. So a lot of things within the receiver were touched to implement IonoGuard. So some more details on IonoGuard. We released it in October of last year, 2023. So we've had it over a year now in the field, and it composed of as I mentioned in the previous slide, a few different things. In the signal processing side, we ensured that we were able to track each signal, each frequency independently. In the past, we were often dependent on L1. Now we can track each independently, so we get more measurements into our engine of each frequency, even if L1 is blocked. Faster recovery. It's important that when the ionosphere is really bad, we can sometimes lose lock. We need to be able to get it back as soon as possible. So that was improved. And then the main improvements were in the RTK engine itself. This is our ProPoint engine, which we released a number of years ago. And this mainly, you can see the name IonoGuard is the guard part of the whole system is at your base station. The base station at a known point can identify ionosphere activity much better. So at the base station, we are identifying ionosphere, the level of ionosphere, and we're sending that those those levels via our CMRX or RTCM protocols to all the rovers. And then the rovers take these additional messages, and you can think of it as weighting the satellites based on the level of ionosphere to improve your positioning accuracy. We also have a mode where if the base is not transmitting IonoGuard messages, the rover itself can actually, from the base station measurements it's receiving, so these could be older receivers or third-party receivers, it can calculate the level of ionosphere from the base measurements and compute improved positions. Not quite as good as having IonoGuard on both base and rover, but that is a mode that we support. And then thirdly, we provide some diagnostics to the user to know the level of ionosphere that they're seeing. On our interface, we have a traffic light system, so you can tell green being good all the way up to yellow or orange and red, the level of ionosphere, and that gives the user an indication of how they're doing. So before we released, we had this data. So these first plots are from data before the October release, using data from Brazil and Sweden. The blue trace is the position, horizontal position, without IonoGuard enabled. The red trace is with IonoGuard enabled. So basically, you can see we're moving it from decimeter level down to centimeter level, which is needed for autonomous operations. We have many operations in mining areas where we have autonomous vehicles that if we cannot trust the position if it goes above a few centimeters, that is a dangerous operation. So, and that would historically have shut down a machine. So with the IonoGuard, they could continue operating. Then our first real test of the system, where we had users in the field with released firmware code, was on May 10th of this year. And then you may have read about this or seen it in the news. There was a lot of press about this. It even has its own wiki page. You can look up Solar Storm of May 10th. And luckily for most of us, because it was evident in mid-latitudes, it was over a weekend, and a lot of users did not experience it. A lot of geospatial construction users did not see it, but a lot of agricultural customers did because they were planting over the weekend. And that did knock a lot of RTK users out for a small period of time. This is a plot from northern Canada where it was particularly bad. In the plot on the left, without IonoGuard, you can see we went from centimeter up to decimeters, and sometimes we were knocked out of RTK completely to SBAS positioning. And then on the right, with IonoGuard, this is the same site, just an antenna split to two receivers with and without IonoGuard. We were doing much better. And then this plot on the right now shows each horizontal line as a satellite over 24 hours. You can see a lot of red on the graph. That's high ionosphere. But even during the red times, you can see some green. So some satellites were not being as affected as much as the others. So we were able to obtain good positioning even during this really bad, using our IonoGuard technology to weight the satellites. A more recent activity was a couple of weeks ago on 10th of October, not quite as big as the May 12th storm, but it was significant enough that even in the lowest latitude of the United States, in Florida, we were seeing northern lights. And then a week later, just a couple of weeks ago, NOAA put out a press release announcing that we're now in actually the peak. We've reached the solar maximum period. And by that, they mean that we should expect to see for the next year or more a significant occurrence of these events. So even though now in the past year we just saw two major ones, we'll probably see them every couple of months going forward. And obviously on the geomagnetic equator, you're seeing it more often than that. But in these mid-latitudes, we could see RTK issues every couple of months for the next year. And this is a plot again in northern Canada for that storm a couple of weeks ago, where we were, going out to decimeters of error, but with IonoGuard at that installation, customers could continue to operate. So just a quick on the benefits of IonoGuard. Obviously, in terms of accuracy, we can maintain the accuracy, centimeter level accuracy continuously throughout through the storm. Increased availability that infers if you can continue to get high accuracy, you can continue to position 24 hours a day, and that improves your productivity. We also have IonoGuard available on all our receivers in the construction, geospatial infrastructure, and obviously the OEM group, which we represent. So that is a benefit. And then I'll put this slide in here just to, one of the main things with ionospheric activity is you need to be prepared for these. Obviously, the best way we recommend is to have IonoGuard technology installed on your basin rover, but obviously not everybody can do that immediately. And until you do that, we recommend keeping an eye on the space weather. The NOAA has a great website, and there they because the activity takes 3 days. Once the sunspots or these ejections from the sun occur, which they can see, it takes 3 days for it to reach the Earth, reach the ionosphere, our highest atmospheric layer. That takes 3 days. So we have warnings, and you can sign up for email alerts on the space weather website. So you can get an email alert and know that we're about to get hit, and therefore you could reschedule projects or whatever needed to do if that are to be aware that you may have to resurvey a point, double check points during that high activity period. Trimble also has a planning website, which using our base stations around the world, we are calculating the levels of scintillation. You can see a plot of that, and we're also overlaid with the satellite constellations. So that's a useful tool also for your planning. So with that, just in summary, I can say that the sun has reached its solar maximum period. We have been warned that we're in the maximum period right now. We are seeing users around the world who are experiencing position degradation, and that is a real unfortunate event that we are seeing, particularly on the along the geomagnetic equator. IonoGuard has proven itself to mitigate many of these effects. We are getting good results in the field today, and that improves our accuracy, availability, and integrity. And with that, thank you for listening. I'll hand it back to Richard. Thank you.
Excellent. Excellent. Thanks so much, Ed. That was a really informative talk, and we encourage everybody to take advantage and utilize those tools to prevent outages and disruptions in workflow. Our next speaker is Jason Evans, the portfolio manager for real-time corrections at Trimble Advanced Positioning. Jason spent the last 2 decades working in the surveying industry, both as a professional land surveyor and as a subject matter expert for optical, scanning, photogrammetric, GNSS, and corrections technologies. Currently, Jason works for Trimble in the Positioning Services Division, managing Trimble's real-time GNSS corrections portfolio of products. Jason, the floor is yours.
Thank you very much, Richard, and thank you to the audience as well for joining us today. Glad to be here and talk about this at such an important time. I think Ed went through some of the biases that we're concerned about earlier in his slides, and I always like to go sort of back to the basics and think about what it is that we're trying to correct. What is it that we need to mitigate in order to have those precise measurements that we expect out of our GNSS equipment? And really, it comes down to these user range error elements of the satellite orbits, the satellite and receiver clocks, and the atmospheric biases. right? And each type of technology, each type of correction that we're doing has different processes to try to mitigate these biases. So if we think about satellite orbits, for instance, so this is when the orbit of the satellite is perturbed, whether that's by the gravitational pull of the Earth, of the Earth's tides, of the moon, or even from solar activity pushing the satellite out of its orbit, we're depending on either being able to simultaneously observe that change at both our base and our rover, or we're depending on being able to model it in a state space representation type methodology. So I've got some screenshots in the slides ahead that show what that looks like when we're modeling it. Likewise, satellite receiver clocks, obviously each of the different constellations has different ground control networks, different time systems, and that's something that we've got to correct for. And finally, those atmospheric biases. So Ed did a great job of showing those scintillation bubbles that you can see out there in the ionosphere. And, in the case of an observation space representation like a base rover solution or a network, we're depending on being able to say, hey, the atmosphere is the same at my base as it is at my rover. And of course, as that becomes less true due to a scintillation event, or perhaps due to the distance of the baseline between the base and the rover, that's something that begins to insert biases into our measurements. So with a state space representation, we have to be able to model the atmosphere. And so I've got some slides ahead that show what that looks like. So we'll take a look and go through those. So when we're talking state space representation, Trimble's technology is referred to as Trimble RTX. So this is a precise point positioning technology. It requires a global network of reference stations. So all around the planet, we have reference stations continuously operating, continuously observing the information, the state of space above, and that information is then sent back to our RTX server software. At that point, we are creating models, creating corrections for the orbits, for the clocks, and creating those atmospheric models that we need to mitigate those biases. In the case of RTX, it is available via both the internet as well as a L-band satellite. So we send that information to one of our redundant uplink stations. It goes to one of the geostationary satellites, and then it is broadcast back down to you on the planet, right? And in that correction information is all that the information that you need to be able to mitigate those biases of your orbit, clock, and atmospheric parameters. So when we're actually looking at what we're seeing on the server side, for instance, these are just a couple of examples at some moment in time where I grabbed screenshots. The one on the top, of course, is the orbit bias. So you see, obviously, as the orbit of the satellite is perturbed, we actually have to be able to measure that and provide a range of that movement in real time. Right, and below you can see the clock bias, and the notable thing I think about the clock bias is, of course, is there's a lot more variability there than you see in the plot above on the orbit bias. So when we're talking about needing to mitigate clock errors and send that information out over a correction stream, we actually have to send it out at an order of magnitude faster than the actual orbit information. So these are two biases that I think we're always forced to deal with. Again, in a base rover or real-time network scenario, we're differencing these, right? We're trying to make these equal to zero because we're observing multiple satellites and multiple signals all at the same time from both stations, right? But when it comes to the atmosphere, of course, things change with our state space representation. We actually have to create a model. So this is an example at just some moment in time when we're looking at the RTX server. On the left-hand side of the screen is the total electron content model. This happens to be a screenshot over South America, what was happening at that particular moment in time. So you can clearly see that there was some increased activity there over Brazil and extending southwesterly across the rest of South America. On the right hand side, this is simply a plot over Europe. So this is our regional model for the tropospheric zenith delay that we're creating. So these models are created. Information is then sent into that correction stream on a per satellite basis so that you can mitigate the impact that the atmosphere has by down at your rover on the ground. Right, and so what does this look like during a scintillation event? So when we're talking about these modeled solutions, we realize that we have a very difficult time of reaching the same level of accuracy as those really short baseline base rover solutions, right? So that's your site base, where we know in a real-time kinematic solution, we're getting a really great answer when we can keep our baseline short and we can keep all the statement of, is the atmosphere the same, true, right? So, but our modeled solution ends up being quite resilient as a result of the model to scintillation events. So over on the right-hand side of these plots, all the way to the right, you'll see that there's some scintillation going on, being measured from our scintillation monitors. You can see in the middle plot the impact that scintillation has on an RTK position. So just like the plots that Ed was showing before, we see that there's some decrease in the precision of the measurement. And of course, then all the way on the left-hand side is the Trimble RTX solution during that same time frame. So here again, this is the shared antenna, two different receivers that are pulling this information in simultaneously. And you can see that with the modeled solution, we're able to mitigate much of the impact from the scintillation event. And really, so the question ends up being, how does this impact me, right? And I know that there are a lot of Trimble users out there that are probably familiar with Trimble's XFill technology. So XFill, of course, is our technology that allows you to continue working in an RTK solution when you have lost your correction stream. Right, so think of this as, I've got a base in a rover and maybe my radio died, or maybe I simply went a little too far and I lost tracking on that signal from the radio that was giving me my correction. In that case, the Trimble receiver will go into what is called the XFill mode, where it actually is utilizing the same correction data that's in the Trimble RTX correction stream. In an XFill mode specifically, it's using the orbit and clock error information to maintain a good position. Now, we cut this off after about 5 minutes because, as you see, you do start getting a little decorrelation here, right? We're not really considering our atmosphere anymore, so it tends to begin. You see these lines at the 1 sigma and 2 sigma lines starting to spread out, right? So this is a pretty common workflow, though. Hopefully, within 5 minutes, you get your correction signal back. You can start picking up your radio and go straight back into your RTK solution. Now, for those of you that have a Centerpoint RTX subscription on your device, which many folks do now that we've been including RTX on 100% of our new receivers being sold since April of this year, you actually have one additional mode that is possible for you to enter into, and that is referred to as the XFill RTX mode or XFill X mode. And in that case, not only are we using the orbits and the clocks, but we're actually using the atmospheric models that are also in the correction stream to maintain a really precise position on the ground. So here again, you can see we remove our correction source, and the receiver actually will switch very quickly into an XFill mode, and then realize, okay, I've also got models available to me, so it switches into the XFill X mode. And here again, you can see your 1 sigma and 2 sigma values flatten right out and stay quite precise. Now, this will continue on all the way until the point at which you hear back for your radio or you reconnect to the internet, and you can get your correction from the real-time network. So, this is probably something that you're going to see. And of course, you can expect that this will also give you the same benefits that we saw on the last slide in terms of being able to mitigate these scintillation events. So pretty terrific solution to have available to you. So at any rate, this is my last slide. I just to reiterate a couple of key points. really, the state space representation that we get with Trimble RTX, the density that we have with our Trimble VRS Now networks, the modeling that goes on for both of those solutions, it is really giving you some good resiliency during these solar disturbances. All right, and if you're thinking about trying out Trimble RTX, or maybe you're just hearing about it for the first time, it does create a terrific positioning insurance for you with those XFIL and RTX modes. So please feel free to scan this QR code and check it out for 30 days if you haven't tried it before. So that's it for me, Richard. Thank you very much, and I'll turn it back over to you.
Excellent, Jason. Thank you for that interesting discussion, and thanks for sharing the QR code. We are going to go into our first Ask the Experts panel. So we've got a couple of questions coming from the audience. This will be kind of a brief kind of interlude, but lots of questions coming. Keep them coming, but here they are. Ed, the first one goes to you. Somebody would like to know, when do we expect ionospheric activity to reduce to a level where RTK positioning is unaffected? Thoughts, Ed?
Yeah, that's a tough one to give an accurate answer, but yeah, basically, in May of this year, we saw our first major storm, which was more than a year before the peak, the predicted peak. So we'd expect it to probably go at least a year beyond the peak. So that's well into 2026. But again, it depends where you are in the world. Customers in South America are probably going to see it even longer than that. It's pretty much a continuous issue there, but it will get less a year after the peak. So, yeah.
Got it. So chronic and persistent is what it sounded like. So as a follow-up to that, perfect entree, what Trimble receivers will support IonoGuard to mitigate all those challenges?
So yeah, I represent the OEM group, so I'm really only can talk about those receivers.
Yeah.
But also within our field systems group, all our receivers that are running ProPoint firmware 6.23 are more recent, and that was introduced October last year. So basically, any receiver, we're all running this same IonoGuard firmware from our field systems, which is our geospatial, construction, infrastructure, and OEM receiver support IonoGuard.
Got it. Great. Thank you. Next question is for Jason. Somebody would like to know, talking about how does Trimble RTX help with ionospheric activity globally? And then we've got some more specific answers or questions from people coming in checking in from both Africa and Brazil. You want to comment on the kind of global coverage, Jason?
Yeah, for sure. So we do have what we refer to as a more sparse network of global reference stations. Those reference stations particularly are used to create that global ionospheric model that we're sending down the RTX correction stream. So in addition to those global reference stations, we also have very dense networks of regional reference stations. So places like the US and Europe and South America, we have these very dense regional networks where we're able to create those higher fidelity, more small scale models. But the global ionospheric model is going to help you anywhere that you're receiving RTX out there on the planet.
Got it. And if somebody were interested in seeing some results from Africa, as an example, what counsel would you provide them?
Well, certainly, I think Ed shared in his slideshow the RF monitoring that we're doing in particular locations. I don't think that Africa is one of those locations specifically. However, of course, we do have reference stations there that are capturing data, right, at all times. So we could certainly look at that data and evaluate it. However, we wouldn't have that raw RF data necessarily. So maybe one of the best things that you could do, of course, is using your Trimble receiver, log a T04 file and share it with the team, for analysis. That would be my my best recommendation there.
Great suggestion for Africa. And in Brazil, you do have you used data sets from Brazil. Somebody checking in from Brazil just wondered kind of what location in Brazil, given the kind of vast size of that country. Any comments on users in South America and specifically for Brazil, Jason?
Yeah, so specifically in Brazil, especially on the Trimble RTX side, we've really been analyzing that area for quite some time. So Brazil has a very dense network of reference stations being used for RTX. And certainly it's an area of interest to our engineering R&D department. I believe the actual RF monitoring that Ed was mentioning in his presentation was taking place throughout Chile, and I think they had some locations over in Brazil as well. So yeah, we've been studying South America, of course, as you saw in the plot that Ed shared of the geomagnetic equator on the planet. There's that dip that takes it right down through South America. So it makes it a very interesting place to watch these atmospheric events go on.
Indeed. Thanks, Jason. I've got one more question, and then we're going to move on to our second poll. And this is for you, Ed. Does the solution include an updated Klobuchar model taking into account your current knowledge of the periodicity of the solar cycles and applicable to all latitudes?
Yeah, good question. Maybe more suited for Jason than myself. But in the RTK case with IANOGuard, we're not updating the Klobuchar model. We're actually creating our own, effectively a model using these ionospheric levels for each satellite and transmitting those to the rovers. But as Jason just mentioned, for RTX, our global network, then we are creating our own models which are being transmitted to the users on a continuous basis.
Understood. Speaks to the quality of the audience, that kind of a technical dive. Jason, anything you'd like to add to that from the RTX perspective?
Yeah, I think Ed did a good job covering it. We're constantly, we've got these centers running. Our network operations teams are monitoring these systems 24/7, and I think there's a group of folks inside Trimble that are keenly interested and keenly aware, of course, of all this stuff going on, and we're certainly paying attention. So.
Indeed. Well, thank you for that. So that's going to conclude our first Q&A session. And now I'd like to turn it over to Lori for our next poll question. Lori.
Absolutely. And on your screen is our second poll question for today. And we'd like to hear from you. What is your typical positioning solution? Select among the following: autonomous SBAS DGNSS, RTK, real-time network or VRS, PPP, Trimble RTX, or post-processed. Coming in at 15% autonomous SBAS DGNSS, 33% RTK, 13% real-time network VRS, 21% PPP Trimble RTX, 19% post-processed. Any thoughts, Richard?
Yeah, this is an RTK crowd for sure. A pretty kind of interesting spread here. Not surprising. Does any of Jason or Ed, would you like to comment on this? Is this kind of consistent with what you see when you're engaging out in the market with various user communities? We'll start with you, Jason, and then go to Ed. Jason?
Sure. Yeah, I think it really varies by the market, right? So if we thought about a construction surveyor versus a cadastral surveyor, we might see some different numbers here, but it looks pretty pretty terrific. Glad to see a lot of use of correction products, and certainly understand the need for those really accurate RTK solutions.
Yeah, indeed. Ed, any different perspective from the OEM side of the world?
No, I think this is what we would expect. Yeah, I think the people calling in today, listening to this, are mainly precision users. So in the RTK networks post-process level of the field. So this is what I would expect, and I think those are the people that are seeing the biggest effect from the ionosphere. Generally, the autonomous people are working more at the meter level accuracy and not seeing as much effects from ionospheric activity. So, yep, this is what we're aimed at. So, yep.
Yeah, that's a really great observation. So thank you for that. Yeah, so, but it sets us up kind of perfectly for our next speaker, who happens to be Corey Spietti, the Chief Operating Officer of Sabanto, with 20 years of experience in agricultural equipment engineering and product management for precision ag technology. Corey earned a Bachelor of Science in Agriculture Engineering from Purdue University. And prior to joining Sabanto, Corey held various roles at the Climate Corporation, CNH, and Kubota Tractor Corporation. His fascination with agriculture was forged while growing up on his family's 1,200-acre grain farm near Evansville, Indiana. Corey, we're delighted you're here, and very much look forward to hearing your perspective on ionospheric scintillation through the lens of precision ag. Corey, please, the floor is yours.
Well, thanks a lot, Richard. I really appreciate the introduction, and I am so thankful for this team at Trimble that is focusing on making GNSS positioning robust and even more usable for autonomy in agriculture. So things I'm going to go through today are we had here at Sabanto, we developed a retrofittable autonomy system that can be added to existing tractors. And I'm going to walk through some of the problems that we've encountered over the past couple of years that led us to the selection of a Trimble GNSS device by the name of the BX992. And so we're going to walk through some problem descriptions, downtime drivers, solutions, how we evaluated it, and then the integration and deployment of that device. So things that we were facing were we had a GNSS device that we were streaming cellular RTK network or corrections into. And when we were working here at our shop in Iowa, we would generally connect to the public real-time network here in Iowa. But then if we took an autonomy system to Texas or to Florida or California, and we weren't using, let's say, a paid RTK provider, and we're relying on public RTK networks, a lot of times we found that our GNSS device was not compatible with the data stream that was coming from those NTRF networks. The other thing that was affecting us was just spotty cellular connectivity. And so when we were trying to use the cellular delivered RTK corrections, if the machine went behind a cluster of trees, sometimes that would block our cellular connectivity, and thus that would hinder our GNSS accuracy. But inconsistent public cellular RTK networks, what I mean by that is there would be occasional outages that we had no control over, nor did we get any pre-warning to that was going to happen. And then if there was a problem, there was no one we could call. There was a lot of times we would call and be sent to a voicemail box, or there would just be an email address, and sometimes we would call on those and never really know if we were going to get support. So the downtime drivers were that the GNSS solution that we were using couldn't elegantly handle momentary RTK signal blackouts. And so I don't know if those signal blackouts were caused by scintillation, but I suspect that some of them were scintillation, but others were caused by cellular connectivity, being blocked by trees, and just if we were working in public areas, there might be a lot of other factors that were affecting us. Also, when our machines were working in areas close to airports and a lot of or military bases or other urban urban areas, we suspect that we were getting a lot of RF interference in our cellular communications that ultimately would handle our ability to consume cellular interrupt corrections. And then another issues that we had were just with our prior GNSS devices was just unpredictable position accuracy convergence times. So we didn't know if it was going to take 60 seconds or 3 minutes or sometimes 30 minutes. This caused a lot of frustration amongst our customers. We even had to it drove us to create additional features that would enable customers to softly restart the device or do other things so that we could attempt to reconnect the GNSS device to these RTK mount points. So the solutions. So just a quick fact about Sabanto. We have a national dealership network, and many of those dealers are Trimble Vantage dealers, and they have visibility of technology that the wider Trimble organization is developing. And although they could not sell the BX992 GNSS receiver, they were aware of it and recommended that we reach out to a representative from the OEM GNSS group. And so once we made that connection, we were able to get a hold of a BX992 device. And that's really when we started the integration of the system. Immediately we were able to see the benefits of the Trimble XFill technology. This really solved our problem of places where we had momentary RTK signal blackouts. We no longer had those issues. When it came to dealing with the RF interference with cellular communications, that pretty much went away because of the capability to consume the Trimble Centerpoint RTX correction. So instead of receiving our corrections over cellular, we were using the satellite delivered corrections. So as long as our GNSS antennas had visibility of the sky, we could rest assured that we were going to get the Centerpoint RTX corrections. And then to battle the unpredictable position accuracy and convergence times, that's where we really saw the XFill technology and the ProPoint positioning engine come to play. Typically, when we boot up the BX992 in our autonomy systems, generally we converge down to 4 centimeter accuracy within 60 to 90 seconds. So this experience, all of those capabilities kind of work together to create a wonderful experience for our autonomy customers. So walking through the evaluation, we worked with a couple different camps within the Trimble Navigation Organization. They had multiple online resources. We recorded and sent many T04 files to the subject matter experts. They helped us analyze the placement of our device on the tractors that are used in the tractors that our autonomy systems are attached to, and they also helped us analyze how much and if there was any kind of RF interference that we would be having with our point-to-point communication systems, so our LoRa devices, and then also our cellular connectivity antennas. And fortunately, all of those things were operating at different frequency bands, and so we had no interference between the GNSS devices and then our communication systems within our autonomy system. As you can see here, we take this autonomy system and we've adapted it to select Kubota tractors, to select John Deere tractors, and also to select AGCO Fendt tractors. And so we're trying to create a solution that we can utilize on different agricultural equipment platforms. When it came to integration, one of the things that was pointed out to us was the importance of power management. And so the pictures that I'm showing here are of the enclosure that we found, and then we have machined, and then we insert the BX992 device into. But we also have I would think a pretty clever power management system. So we have a voltage regulator board that has some capacitance, and so why is that important? It's whenever you try to start the engine of the tractor, and a lot of these smaller tractors that we're on, a lot of times the amperage gets drawn down to a point where it can cause the GNSS device to brown out. Which you do that so many times, it's really hard on the device. So we utilize the CAN message payload to that carries the position information between the 992 receiver and the autonomy controller on our tractor. And then we have an Ethernet connection between our autonomy controller and the BX992. And that allows us to remotely access the BX992, but leverage the cellular connectivity of our autonomy system. And then before we ship out an autonomy kit to one of our customers, we go through a process of provisioning the device and adding all the permanent unlocks to the device, so that when the client or the dealer installs it on the tractor, it's pretty much ready to just plug and play. So deployment, one of the big things for us was the capability to remotely access the 992. And so because of this remote access capability, we as I'll say an OEM can manage the subscriptions on behalf of our customers. We can check and see if everything is running correctly. And then in the instances where they may need to recalibrate the system, we can remotely walk them through the process of how to handle the equipment, and then we can do all the button pushing within the Trimble GUI. So that's worked out very well for us. And with that, that's the conclusion of my presentation. I want to hand it back to Richard.
Corey, thanks so much. Really interesting talk. I appreciate that real world experience. So now I would like to introduce our final speaker, Joshua Goodwin, Director of Autonomous Center of Excellence for Flanders. Joshua has spent the last decade in the mining industry, specialized in advanced technologies. Recently, he's concentrated on the development and deployment of the Flanders Aardvark autonomous drill control system. This experience has given him firsthand insight into how various technologies can enhance the value for mining companies. We're delighted you're with us today. Joshua, please.
Cool. Thank you very much, Richard. It's my pleasure to be here today to discuss how Flanders has worked closely with Trimble to work on the challenges that we've seen with our customers around scintillation and what solutions we put in place to deal with that. So what I'll be running through today is just to give everyone a bit of an overview of our Aardvark product from Flanders, just to get people to understand what it is and what the importance of the GNSS technology is for us. And then a bit around the problem statement that we had with our customer, and then how we came up with a solution working with Trimble on that, and then the performance tests that we saw there. So what's Aardvark? So Aardvark is our control system, our autonomous drill control system made by Flanders. So what that does is that allows us to put our autonomy package on any OEM blast hole drill, and then be able to operate those machines from a remote location. The operators are able to operate 1 to 8 drills at any time, and then the system will go through all of the functions. So it'll position the machine at the hole, it'll level it, it'll drill it, then it'll de-level it from there. So what do we install on these machines? So we put our autonomy piece. What that includes is it includes our control systems, cameras, hazard detection systems, IO modules to control. But most importantly, what I want to talk about today is the GPS antennas. So we'll install some GPS antennas and the receivers on board the machine, and then we'll connect to the the client's mine site's base station and receive those RTK corrections from there to get our high position GPS. Now, high position GPS is very important for a number of reasons around the drilling space and our autonomy space here. So the key ones there are we want to accurately position ourselves over the hole. So the blasting engineers will design the holes where they need to be so that they can blast it to get the correct fragmentation, which is important for downstream processes, including the digging, the hauling, and the processing at the end. If the dirt's too large, then it's harder to dig and harder to haul, harder to process. If it's too fine, again, becomes harder to dig, harder to process. So it's really important that the machines are able to position themselves exactly where the designs have been placed and then drill to that correct elevation that's on there. So we need to have that centimeter level accuracy. But then, so that's from a production point of view. Then it's also very important from a safety point of view as well. So you've got these machines operating autonomously in an area where there's high drop-offs, there's high walls, there's other machines in there. So we'll have machines will operate in an autonomous operating zone. So we've got boundaries that the machines need to operate within, and then the machines need to come close together to each other. So we use GPS as one of our factors to provide that safety. So without high precision GPS, we're not able to move the machine. So this becomes very important that we have that RTK fix at all for as much time as possible when we're operating. Because if we don't have that RTK fix, then what we've got to do is we've got to stop the machine from moving, which is then going to cause problems down to our end customers. So we had a problem at the end of last year with scintillation. So we had one of our clients in South America from a period of August to December in 2023, they were seeing significant impacts due to the scintillation. I guess as the speakers before me have said, it's only going to get worse. So during August to December, what the impact that they saw is they saw a total of just over 1,000 hours of downtime across their fleet due to the scintillation. So they're running a fleet of 9 machines. So 1,000 hours of downtime that resulted into 28,000 lost meters. Now, what does that equate to the customer? That actually equates to 4.16 million tons of ore not being extracted. Now that becomes super significant to their mine planning, their operational efficiencies, and at the end, just the profitability of the site. So it was very important for us and the customer and our customer to work out a solution to get past this, because as they knew in December 2023, it was only going to get worse. So those numbers are only going to get higher. So we needed to figure out a solution on how we could get past the scintillation. So that's where we contacted Trimble. So in January of this year, our engineering team reached out to Trimble and their engineering team. We've been working with Trimble for quite a while now, running Trimble receivers on some of our machines. So we pretty much went to them and said, "Hey guys, what have we got for a solution here?" So that's where they told us about the IonoGuard solution, and we worked with them to figure, okay, how do we apply this as quickly as possible to our machine? So what did that look like? So we upgraded the base station firmware. So we worked with our client and they were running a Trimble base station. We updated the firmware on that so that it could incorporate the IonoGuard. We had a BX992. We didn't have one on the machine that we wanted to do the testing on, so we installed one on there as well. So put that on one of the 9 machines that we were running autonomous on this site. We enabled the IonoGuard feature onto that. We went through, adjusted all of our configurations on the machine, redid all our safety validations to ensure that we were still getting the accuracy that we needed, was getting the reliability that we needed, and everything from there. So then we went into and started doing some performance testing. So we ran a quick 15-day trial just to give us an idea of if we were going to see an improvement or not, and we were very, very impressed with the results. So over that 15 days, on every single one of those 15 days, there were instances where the other machines that we had running on site that didn't have the IonoGuard feature on it, they had system outages due to scintillation. So throughout the day, there were instances where those machines were down for 1 to 2 hours. But the machine that was running the IonoGuard system, it was able to keep operating. So our picture on the right here shows two of the other machines that were operating in the same location. They didn't have the RTK fix, so those machines had to stop operating, but the machine that had the IonOGuard system enabled, it was able to continue operating throughout that. So we saw that on every one of the 15 days. And there was actually no downtime on that machine due to scintillation at all during the 15-day period. So this was something we were super impressed with. We thought that the IonOGuard was going to reduce the impact of scintillation, but effectively during the test period, it was able to eliminate it altogether. So it was also noted that during that test period, we did see some high levels of that scintillation. So it was very good to see that it was the system was able to work through that, especially given we're going to see more and more of this going forward. Okay, so in conclusion, we found some massive improvements by seeing the IonOGuard functionality. It exceeded all the expectations that we had, especially being able to utilize receivers and equipment that we've had on the machines already, and just being able to do some firmware updates and to enable these additional features. So that's was able to prove that we can have our autonomous systems running during these periods, which is really important to our clients. And it showed that we can work with our clients, but then also working with Trimble to come up with the solutions to these problems that we're seeing every single day. So what we're doing right now with this client is we're actually upgrading the machines that have BX992s already, or installing them on the machines that don't with the IonOGuard functionality to not just the rest of the fleet of machines that they've got at that site. This company's also got multiple fleets throughout multiple sites with fleets throughout South America. So we're going and installing them everywhere there. So that's the conclusion to my presentation. I'll hand it back to Richard.
Joshua, I want to thank you for that really interesting discussion, and pretty amazing when you consider the real impact of those disruptions on workflow, and the value of that is really significant. So I appreciate you drilling into that. Now, on your screen, you'll see a number of resources that we'd like to provide, and we encourage you to, if interested, get more information at these various links. Know that these links will be sent out in a follow-up thank you email, so you don't have to write them down, but just want to make you aware of them. And now we'd like to conclude with one final poll question. Lori, could you get a poll up in front of us, please?
I would be happy to. And on your screen should be our third and final poll for today. And we'd like to know which aspects of your positioning solutions are most important to you. And this is on the honor system here. If you could give us your top 2 choices among the following: accuracy, availability or convergence time, integrity or confidence in positioning output, reliability, or support. So again, go ahead and give us your top 2 selections here. Coming in at 64% with accuracy, 32% availability, convergence time, 51% integrity or confidence in positioning output, 37% reliability, and 15% support. Richard, any thoughts here?
Yeah, accuracy continues to be addictive for sure, but our panel and I think is going to be delighted in seeing that integrity is a second highest rated importance in terms of the quality of the positioning. And any comments from our panel? Jason, Ed, Corey, Joshua, any thoughts? How does this data kind of comport with your experience? Any comments, gentlemen?
Yeah, I think this is what we'd expect. Definitely in terms of confidence and integrity, we've seen increasing demand for that as we get more into autonomous operations. It's very important that you're confident in the positions. It's great to have them very accurate, but if you have no confidence, then it's a hazard in an autonomous operation. So yeah, I think this is what we would expect.
Yeah, and so I just wanted to kind of set that up as a kind of prelude and a transition into our Q&A. So our Q&A, we've got lots and lots of questions coming in, kind of flying around from all over the world. The first question will be for you, Corey, and somebody would like to know, how does Sabanto handle the GNSS receiver integration to different size vehicles? How do you actually physically attach and integrate those solutions?
Yeah, so in the presentation there was that enclosure box that I showed, and then typically what we do is we create we have a bracket system that places the GNSS receiver enclosure and its two antennas is on the highest point of the machine. And we try to keep typically the GNSS antennas, they're about 1.25 or meters or more apart, so that we don't get any attenuation between the GNSS antennas. And then when we're provisioning the devices, we typically know what tractor, what machine the system is going to go on to. So we enter in all of the physical offsets that we know and record when we're building the first autonomy kits for a specific machine model.
Okay, great. Corey, I'm going to stick with you for just a second. Somebody would like to know, how reliable have you found the RTX signals to be? And then also as a follow-up, what happens if an RTX beam goes down? Any experience with that?
Yeah, so we've found the RTX signals to be extremely reliable. Very rarely have we had an instance, I think, where we've lost position accuracy. I'd say probably our biggest issue is kind of training our customers to actually keep the machines sitting still while the GNSS position is converging. And then what was the second question?
Just they wanted to know if the specifically what happens if an RTX beam goes down.
Yeah, so we have experienced that a couple times, and speaking with the Trimble support team, they've just simply had us remote into the 992 device that was having trouble, and we've set the beam to the Latin American constellation. And by doing that, that's allowed us to keep running. And then once we get, once I'll say the issue with the beam is resolved, they notify us, and then we can remote back into that GNSS device and switch it back over to the North American beam.
Got it. Really interesting. Touching on two of the other five of the qualities of precision and both reliability and support. So let's move over to Joshua and get another kind of user perspective. And Joshua, do you see IonoGuard functions valuable to some of your other customers, in addition to the use case that you've described?
Yeah, we sure do. We've got a number of our machines operating throughout South America. So we're having discussions with them. They haven't seen the impact as much, or I don't think they've understood that the impact that they're seeing due to the loss of GPS is due to scintillation. So we've started having those discussions with them to help them understand that. And given how easy it is for us to implement the IonoGuard functions onto the machines, it's a function we definitely see value there to all of our customers.
Yeah, I mean, given the given the success that you've described, and then sticking with you, Joshua, as a follow-up, what do you believe is the most valuable part of the IonoGuard function? What's been your experience so far?
Yeah, the most valuable function would be just how easy it is to implement. All you've got to do is upgrade the firmware on the receivers, unless you've got the firmware already past the point, and then it's just enabling it, which makes it super easy to do, and then you get that additional functionality. And I guess what our results showed is just how accurate it is in being able to remove that scintillation. So as the poll shows, it means that we can be super confident and super we've got that reliance on it, so we're super confident that that position we're getting is going to be the accurate position all the time. So yeah.
Excellent. Great. Well, thank you. The questions are coming in fast and furiously. Jason, this one's for you. Will the exfil corrections be available on receivers that are part of the RTX 100% attach program? Somebody would like to know.
Yes, so definitely. In fact, anyone who has a subscription to Centerpoint RTX will always have that mode made available to them as well. So on the receivers that are part of that program, that would be included at no additional charge. So you would definitely have access to it.
Yeah, and as a follow-up, somebody would like to know, what's the minimum firmware version required for IonoGuard? And is IonoGuard a separate option or included with a certain minimum model? Could you walk us through that a bit?
I can answer that if you want.
Yeah, please.
Yeah, certainly. Yeah, as I said, we released IonoGuard in October last year, and that was with firmware 563 or 6.623. So you need to have a ProPoint receiver, a receiver running ProPoint firmware, and ensure you have this 523 firmware. So any customers on within their firmware warranty can upgrade to that. There is no extra charge for that as long as you're within the warranty period.
Very good.
Yep.
Well, thanks for that, Ed. And let me pose this to both Ed and Jason. How much error would you expect in an RTK solution with a 2-kilometer baseline without your technology?
So that would be an RTK baseline. Yeah, again, it depends on the level of scintillation you're seeing, but we've seen it up to over a meter in really bad times. But typically, it's at the tens of centimeter level. A lot of our customers have thresholds. So if the position accuracy goes up above maybe a 5 centimeter level, they will shut down the machine. So yeah, even on a 2-kilometer baseline with ionospheric disturbances, we go above the 5 centimeter level without IonoGuard quite regularly. So yeah, just as I said, these bubbles are very localized, so your base can easily be seeing a different part of the satellite can be going through a different ionospheric path than the rover. So even on a 2-kilometer baseline, we will see errors of up to decimeters.
Very good. And then while I'm sticking with you, Ed, for just a moment, does one require a different IonoGuard firmware settings for equatorial versus northern latitude operations? Could you talk about that?
Yeah, good question. No, it's the same firmware for worldwide. So, so the algorithms can identify the type of ionospheric interference and produce these specialized messages in our CMRX or RTCM format. So yeah, no, you do not have to adjust the base or the rover depending where it'll handle it automatically. So you're good.
Excellent. This next question is for you, Jason. And if you could kind of, and I'll probably put this out to the full kind of panel. And so what about the effects of the ionosphere on L-band corrections themselves? Somebody would like to know. Jason or Ed, would you like to begin?
Yeah, I think that the L-band correction certainly could be disturbed. However, you have to think of it in terms of you're getting these components in this correction stream, right? So as long as your latency in getting each of those components, like your clock correction or your orbit correction, as long as that doesn't increase too far to such a threshold that the information is old and not usable, then you'll be in good shape. So in terms of, is it different than perhaps when you're thinking about a GNSS signal? When you think of a GNSS signal that we're using for a carrier phase range measurement, right? We need to be able to create a copy of that. And we need to have strong correlation between our copy and the signal that is coming from the satellite. And so that it's kind of a different situation there in between, in terms of matching this carrier phase versus getting the data that's on that correction stream in the L-band. So just two different things to think about. When the wave front is perturbed of that carrier wave as it's coming down and it hits the ionospheric scintillation bubble, that's going to impact our ability to carrier phase range, right? Versus getting the data off from the L-band correction stream.
Got it. And then to kind of follow up on that, Jason and Ed, can somebody like to know about? Can you kind of provide a little bit of clarity about the disturbance? Is it for solar disturbances or ionospheric disturbance? Somebody would just like to you unpack that just a bit. Ed, Jason.
Yeah, I think it's the same thing. I mean, solar disturbances, this space weather is causing disruption of the ionosphere. When it hits the ionosphere 1,000 kilometers up, when the radiation comes from the sun, it's disturbing the ionosphere, and that's what the GNSS signals are passing through, and we're seeing a corruption of those carrier phase measurements causing the inaccuracies in our position. So I think it's the same thing we're talking about there.
Okay, all right. Just wanted to clarify that. Somebody else would like to know, and this is for Ed and Jason, but love to hear from Joshua and Corey as well. And this goes back to our last poll question, talking about integrity and saying, how is it implemented on IonoGuard? Can you talk about integrity as it relates to the IonoGuard solution? Ed, Jason first, and then maybe we can talk about the experience from your customers.
Yeah, so integrity is an integral part of our ProPoint solution. So for every epoch, every position we output, we associate an error confidence level with the position. And that's what we spend a lot of our time running through data sets around the world, trying to make sure that that what we put out is an accurate estimate of our error. So yeah, it has been tuned to allow for IonoGuard and improved for when we are running in IonoGuard mode, that the integrity of the solution is as accurate as possible. If Jason wants or anyone else wants to add to that.
Well, I would add to that from the infrastructure standpoint. So when we're thinking about our global reference stations that are making our corrections products, for example, we're also dedicating a certain number of those resources, those reference stations, to specifically track the integrity of our solution. So those receivers, those reference stations, act almost as a client, right? They get the correction information, they compare it to their known position, and they send that information back to our servers. And that information is then evaluated to make sure that we are getting a good position. And the correction data that then is output is flagged with its integrity values. And once that information reaches those stations again, they validate that they actually received that information. So I think there's two separate components here when we're thinking about like Ed was talking about at the receiver level, but there's also the components from the correction level where we think about our infrastructure and how we're doing integrity checks there. Excellent.
Thanks, Jason. So the questions continued to come in, lots of interest, but unfortunately that is all the time we have for today. And what I'd like to do is just let's go around the panel in order of speaker presentation, and let's ask for, I'd like to ask for some concluding comments, having just spent the last 90 minutes together. Ed, any final observations?
No, I'd just like to thank everyone again for attending the webinar and asking those great questions. Definitely reach out to us direct if you have any specific questions. We can try and answer those. But no, and thank you to our fellow speakers who did a great job in their presentations. Thank you.
Yeah, great. Thanks, Ed. Jason, concluding remarks.
Yeah, I think in Ed's presentation, he gave some web resources, space weather and GNSS planning. And, I just, I want to point out to everyone that this is the time to be really thinking about your workflows and making sure that you are informed of these events. And that's a great way to be protected against them, as well as having these technologies like IonoGuard and Trimble RTX available to you. And just like Ed said, thank you everyone, for being here today and taking part of this webinar.
Yeah, thank you. Corey, final comments.
Yeah, I just want to say thanks to my fellow panelists here, and thank you to Trimble, because there's two things that enable our autonomy, and one of them, one is cellular connectivity, but without good, accurate GNSS positioning and technology, we're sitting still. So thank you very much.
Great. Yeah, thank you. And then finally, Joshua.
Yeah, I'd like to thank the other panelists and thank you, Richard, for facilitating the opportunity for us all to talk. Also, yeah, I'd like to thank the Trimble guys and that around being able to work with them closely and be able to come up with a solution that can help us all. So thank you all.
Yeah, good stuff. So inside GNSS, we have covered space weather and solar max and ionospheric scintillation for a very long time. This solar max we're approaching, and I got to tell you, this ensemble of perspectives, hearing from mining, hearing from agriculture, hearing from Centerpoint RTX, the corrections perspective, and hearing from the OEM, and that ensemble of perspectives with the kind of IonoGuard as the through point was really impressive, gentlemen. So thank you. I want to sincerely thank our panel for an outstanding and informative discussion today. That's all from here. So Lori, could you wrap us up, please?
I'd be happy to. Before we sign off, would like to thank each and every one of you for joining us and trust that you found today to be of value. Special thanks to our distinguished panel members and, of course, our sponsor and co-hosts Inside GNSS, Inside Unmanned Systems, and Trimble. Again, thanks for joining. This is Lori Dearman saying, hope we see you on the next one. Bye for now.